Okay, folks, we're back. This is section 6-2. This is video number 2. My video number 1 ended very awkwardly and prematurely. I had some technical difficulties, but I believe we're okay now. All right, so here we are. Where we left off, we were talking about how we go from the x values, the original data values, are transformed into z values. And here's an example that he wants to share with you. Now, you psychology majors might recognize this. This is what we used to call an IQ test. The average IQ was 100. So we've got 10,000 kids that we took their IQ test. We find their average, we find their mu was 100. We also find their standard deviation, which happened to be 15. Okay, so 100 plus 15, this is your 1 sigma here. This is mu plus 1 sigma. 100 plus 30, that's 100 plus 2 times 15, that's the 130 there, okay? So these are the scores for a standardized test. It's an IQ test. Let me adjust this. All right, he's talking about this standardized test. He's talking about an IQ test, as I say. It has a mean of 100, has a standard deviation of 15. When you transform, so here they are. So here's my x values down here. Average of 100, 115, and so forth. Okay, when the scores are transformed to z values, these two distributions will coincide. Each one of these x values has now been changed into a z value, and they coincide. But now the curve is, instead of having a mu of 100, has a mu of 0. Instead of having a standard deviation of 15, it has a standard deviation of 1. So this right here, this is mu plus 1 standard deviation in the z transformation, or the z values. This is the mean plus 2 standard deviations in the z variables. So you got the same curves correspond to z values and to the x values. So the two distributions coincide. Okay, the z distribution has a mean of 0, there it is, and it has a standard deviation of 1. Okay, so now what he's saying is, okay, listen, we got a procedure now. We're going to have an algorithm for how we're going to do this. Okay, we can find this area under any normal curve by transforming the values of the variable to the z values. So it doesn't matter what you start out with. The x that you started out with, it can be IQ, it can be height, it can be weight. This next example is going to be liters of blood. It doesn't make a bit of difference. If the x's are more or less, approximately normal, you can transform them to z values, and now we get a nice, easy way of doing this calculation. So how do we do it? We draw the curve. We convert the values of x, those are my original data points, we convert them to z values using this formula, and then we find the corresponding area, and we can use a table, we can use a calculator, or we can use software. It makes no difference what we use. They get the same answer, obviously. Okay, so now we're going to talk about an example here, liters of blood. So this will be good for all of us nurses in here. An adult has an average of 5.2 liters of blood. There it is. The average amount of blood for an adult is 5.2. We're going to assume that this variable, the variable is liters of blood, or quantity, how much. The variable liters of blood we assume is going to be normally distributed, and we say that it has a standard deviation of 0.3. Find the percentage of people who have less than 5.4 liters of blood in their system. Okay, so it seems like a reasonable thing that we want to do. So we draw the curve. Here it is. This is my x values. My x has a mean of 5.2, and it has a standard deviation, what did he say, of 0.3. What I want is how many people are less than 5.4. Okay, so this first curve here is just to kind of help us understand the problem. The next step, find the z value corresponding to 5.4. Now, the reason we want that is because we want to know what is this cutoff point here? What is the, we want to find out what is less than 5.4. We don't have a table for that, but we do have a table for the z values. So 5.4 corresponds to, here it is, you do the arithmetic here, x minus mu over sigma. So 5.4, take away 5.2. 5.2 is my mu, divided by 0.3. Do the arithmetic, boom, there it is, 0.67. Therefore, 5.4 in the x values is now 0.67 in the z values, in the z scores. Okay, so it is 0.67 of a standard deviation above the mean. That language there is a little bit confusing. What he's basically saying is, hey, we're going to use the standard deviation as our yardstick. See, there it is right there, the standard deviation, 0.3. So it's 0.67 of a standard deviation. If you think of this the sigma as being in the yardstick, how far over are you? You're 0.67 of one of one standard deviation. Sorry, I'm having technical difficulties. Okay, so the standard deviation we're talking about is a standard deviation here, the sigma of the original data points. Okay, it would be, and that has to be true because the standard deviation of the z scores is 1. That's part of the definition. Okay, all right. So I hope I didn't confuse you there. Oops, I'm sorry. Okay, all right. So there it is, 0.67. The next step, the final step, is you find the corresponding area in the table. So you go to the table and you look it up. And I did that one or two videos ago. I did that. I just don't have time to do that again. So make sure you know how to do that. You look at the table, you find the 0.67, you find out how much the area is, and you find out that the amount of the area is 0.7486. So in other words, 74.86% of the adults of this population are to the left of 5.4 liters. Okay, so do you see what's going on here? Is that you're not answering the question directly. You're going to the z scores and you're answering the question in the z score space, in that separate universe. You're answering the question, but the answer is the same. The answer you get in that alternative universe of the z-scores is the exact same answer as in the original universe of the liters of blood. Okay, so now another typical type of a problem that you'll want to know is you'll want to know how much of this variable that you're dealing with, how much of it is between this number and that number. Okay, so now here's the example we're dealing with here, but it could be any number of things. This is just a metaphor for other kinds of problems that we're going to get. So monthly newspaper recycling. Okay, you get an average household generates 28 pounds of newspaper for garbage, for recycling. Okay, it's normally distributed. It has a standard deviation of 2, and you pick a household at random. So just some random household has everybody has an equal chance of being chosen. That's what we mean by random. And we want to find out what's the probability that it generates between 27 and 31 pounds per month. So between 27 and 31 pounds. So this kind of represents the population between 27 and 31. On average is 28. Okay, the mean is 28. But how would you figure out what percentage is between 27 and 31? Well, fortunately, we have statistics to figure that out. And then that's problem A. Problem B is more than 30.2 pounds. Okay, so let's take a look. Always, if you don't do this, you're being very foolish. Draw a cartoon. Draw this picture to help you visualize what's going on. So we draw the cartoon. We want to know between 27 and 31. 28 just is the mean. It happens to be in that interval. We do those two calculations. Now you see what's going on here is that we've got z sub 1 and z sub 2. In other words, we're going to have a z-score that corresponds to 27 and a z-score that corresponds to 38. Or I'm sorry, it corresponds to 27 and one that corresponds to 31. So Z1 corresponds to the 27, Z2 corresponds to the 31. That little subscript there just tells us, hey, this is the first one I'm doing, this is the second one I'm doing. It's just a way of identifying it. Okay, so now to find the appropriate area, you have to find the area to the left of Z2. Okay, Z2 is 1.5, that's right here. Z1 is right here, that's the Z1 is negative 0.5. So remember, the tables only give you the area to the left. So you find the area to the left of this guy, you find the area to the left of this guy, you subtract them, and that gives you the area that's in here. So the best thing you can do is draw cartoons on this, and you'll see exactly what I'm talking about. Okay, so now to find the area to the right, let's go up here a little bit. Okay, give me a second here. This is harder than it looks. Solution B. All right, so I'm on solution B here. I draw, this is for problem B. I draw the cartoon, and what I'm looking for is the amount of garbage that's 30.2 or more. So here's 30.2 or more. So I draw my cartoon. That helps me visualize this. I get my corresponding Z value. My corresponding Z value is 1.1. So now I draw that cartoon. They're the exact same shape. Everything looks the same. They correspond to each other. So here's my Z scores. 1.1 corresponds to the 30.2. So now what I want is the area to the right of 1.1. Looking at my table, my table tells me what is the area to the left of 1.1. So I take that area and I subtract that from the entire amount of area. So I'm not going to do it again. I've done these previously. Okay, I hope that is clear. Okay, let's see here. I think that covers that. There's no easy way to pause this. I'm sorry. All right. Solution B, you draw the curve. All right, I think that's pretty clear. Okay, so folks, I'm going to have to leave the rest of these examples to you. Work your way through the examples. You got to do it. You got to work your way through it, pencil and paper in hand. This problem here, example 6-8, that is a little bit different. That's a different problem than what's in the book. So let me go ahead and do 6.8. Remember, I'm using this PDF version. It's edition number 9. The textbook is edition number 10. So some of you might have edition number 10. Edition number 10 has a different problem for 6.8, but it's exactly the same concept. The amount of electricity used by a PC. Okay, desktop PC uses a certain amount of watts, on average 120. Assume the variable is approximately normally. Standard deviation is 6. If you pick 500 PCs, approximately how many will use less than 106 watts of power? Same concept we've been doing all along. Draw the curve. 106, this is in the X universe, not X-Man universe, the X universe, the original data universe. Find the Z value. That's negative 2.33. So here's my corresponding curve. I go to the left, so it's from the table, it tells me it's 0.0099. Okay, there it is. So now it's 0.0099. That's the probability, or that's the fraction that you expect. So it's 500 times 0.0099 gives me 4.95. So we round it up to 5. So approximately 5 PCs use less than the 106 watts. Okay, then his final comment here is, when you're using percentages, use a little common sense. You write the percentage as a decimal before you multiply. And then you round it to the nearest whole number, since it's not possible to have 4.95 PCs. So that's just common sense. Okay, so that's the end of this video.